So now that we've kind of talked individually about SN1, SN2, E1, and E2, and in our last set of videos talked a little bit about like some direct comparisons, like what could force something to go E2 compared to SN2. I wanted to do kind of a summary video that kind of walks through and kind of does a direct comparison between a lot of the kind of key characteristics which we've been talking about and all of the different reactions. So one of our first ones we'll start with is our kinetics, or our rate of our reaction. The order of the reaction is going to be corresponding to the number in the name. So our 2s, SN2 and E2, are both going to be second order. And being second order means that their rate is going to equal to a rate constant times the concentration of both of the components. That is going to be our substrate, which is our R leaving group, and then either our nucleophile or our base. If it's more nucleophilic, it's going to go SN2, more basic, E2. For our 1s, so our SN1 and our E1, they're going to be first order. That first order is only going to have dependence on our substrate. So we are not going to have any kinetic terms that are going to be associated with our nucleophile or our base. And SN1 and E1 are going to have the exact same rate law. It's going to be rate equals our rate constant, Kr, times the concentration of our substrate. That is our R leaving group thing. That is one of the reasons why you'll see SN1 and E1 kind of happen simultaneously in most cases, because the rate determining step, which is what we describe through our kinetics, is going to be the exact same for both of them. Now, one of the first and most important things that we're going to be thinking about when we're trying to decide between all of our reactions is going to be our substrate. And for our substrate, that's going to be our electrophile. There's going to be an electrophilic carbon that's going to be connected to the leaving group. We're going to be thinking about what is its substitution. Substitution being how many carbon stuff is surrounding it that can either get in the way with sterics or help stabilize electron deficient reactive intermediate. If you have a methyl substrate, that is going to strongly favor SN2. You're probably going to go SN2 and there's not any other traces. If you are a primary, you're also probably going to go SN2. The only kind of caveat is if you have a very strong base, then you can do an E2 elimination, but you do need a really strong base to overpower the substitution. If you are secondary, it can be literally everything. Secondary can go SN1, SN2, E1, and E2. So secondary doesn't help at all. If you're going to be tertiary, you're not going to be SN2 because that's going to be too crowded for the backside attack. And you kind of have potential for your SN1, E1, or E2. So you can substitute or eliminate. The eliminations are both fine because you'll have a more substituted double bond, which would be more stable based on Zaitsev's rule. One of the differences between whether or not you're going to go like your SN1 or your like E2, for example, is going to be, do you have a strong or weak base? When we're also thinking about our allylic and benzylic structures, allylic and benzylics will actually help favor our SN1 and our E1 because you're making a more stable reactive intermediate. In allylic structures, you can also have a little hyperconjugation for things like SN2. But if you have, for example, a allylic primary or like a benzylic primary, they would potentially favor your SN1 more because that's going to be a very stable reactive intermediate that you can form. The next, and is going to be relatively important, is going to be our nucleophile or our base. That's going to be the thing that does the attacking. In our 2s, both SN2 and E2, we are going to prefer a strong nucleophile or base. And we know that it is strong based on it being charged. If you see a negative charge, that's a good hint that you're going to be doing a 2. We can sometimes hide our negative charge. So for example, if we used NaCN, Na for sodium, that doesn't look like it's charged, but when you put that in solution, that's going to be a salt that dissociates and then gives us our Cn minus. So sometimes we'll kind of like hide the charged species with a a spectator ion are group 1 or group 2 element in a salt form. So either of those, either physically charged or with a ion, are both possible. Now, the difference between your SN2 and your E2s are going to be, do you have more nucleophilic properties or more basic properties? And we're going to show, and that's going to be the propensity to, if you're a nucleophile, it's going to be your propensity to attack carbon. If you're more basic, it's propensity to abstract a proton. We're going to talk about some examples and some common ones. I have some listed down here, and there's going to be some more in another table, which we'll go about after this. That we'll actually think about a little bit more about pKa. But a lot of our halogens, so our chloride, bromine, iodides, are more likely to go SN2. A deprotonated carboxylic acid is going to be more likely to go SN2, and you kind of have a few others there. So cyanos, sulfates, amines, those are more likely to go SN2. Your E2s are going to be more likely to be bases, so a alkoxy, a hydroxy, T-butoxide, which is going to be a bigger, bulkier base, as well as things like LDA. LDA is a good base. For your 1s, your SN1 and your E1s, the strength of your nucleophile is a lot less important. And if you really want to promote the 1s, often you'll choose a very weak nucleophile or base, and those are going to be ones that are going to be protonated. So like methanol instead of like a methoxide, ethanol instead of an ethoxide. So if you see things that are not charged and instead are protonated, those are going to be weaker nucleophiles and bases and much more likely to favor our 1 reactions. Now, as we kind of continue on some of our other groups, our next is going to be thinking about our leaving groups. So all of these reactions are going to require good leaving groups. I have a bunch of examples of good leaving groups. Often we're going to see halogens, so iodide, bromine, chlorides. We do know that alcohols are not good leaving groups, as we've kind of shown in green, and that's a mantra that I've been trying to repeat as often as I can. And because of the fact that alcohols are not good leaving groups, we are not going to see them very often. And if we do, we can actually transform them into something else. The oxonium in acidic conditions, or something like a methyl or a tosyl group under basic conditions can both work. You can also have leaving groups that are maybe a little bit worse, ones that are big and bulky, like a quaternary amine. Those are going to be more likely to do things like Hofmann elimination. Now, when it comes to solvents, one of our key criterion is our solvent needs to be able to dissolve our materials. And with most of our groups having a dipole associated with them from the leaving group, we are strongly going to prefer polar solvents. And polar solvents are going to follow our kind of rule of like dissolves like. A lot of our choice of our solvents is going to be whether or not we want them to interact with our materials. For our 1s, like our SN1 and our E1, we want the solvent to solvate or surround and interact with our reactive intermediate, our carbocation. So polar protic solvents, those that can hydrogen bond, are going to be really good solvents for our 1s. Typical examples of polar protics are going to be things like water, methanol, ethanol, acetic acid, ammonia, tert-butanol, so on and so forth. For our SN2, our nucleophile needs to come in and attack. And if it is, then that is our charge component. Typically having a negative charge is going to be a strong nucleophile. We do not want our solvent to go and surround our nucleophile in an SN2 because that's going to be unfavorable. That's going to slow down our rate of reaction. So for SN2s, we are going to prefer polar aprotic solvents. Those are going to be solvents that cannot hydrogen bond. So they're going to still have a lot of alcohols they're going to have a lot of oxygen and nitrogens. However, they're not going to be alcohols or amines, no hydrogen bonding. So ethyl acetate, DMF, DMSO, acetone, THF, chloroform, DCM, acetonitrile, and many more are kind of examples of polar aprotic. Now, for an E2 elimination, you really just need a polar solvent. However, we know that E2 and SN2 are going to compete a lot. So if you want to promote your E2 and suppress your SN2, often you'll choose a polar protic solvent for your E2. That protic solvent is going to suppress any of your side reactions of your SN2 and really help promote your E2. So those will be generally preferred. The next thing we'll talk about is our products. So in a nucleophilic substitution, either an SN1 or SN2, you're going to form that same general product where we are going to be replacing our leaving group with our nucleophile. In a elimination, whether E1 or E2, we are going to deprotonate a carbon that's going to be one away from our leaving group, and then kicking out our leaving group to make a double bond between our carbon that's one away and then our electrophilic carbon where that leaving group is attached to. We also talked a lot about the stereochemistry, thinking about how things are situated in space. In our SN2 reaction, there's going to be an inversion of our configuration because of the fact that it's a backside attack. That means at the location of the attack, if there is some defined stereochemistry, like a wedge, for example, when that backside attack happens, our group is going to be added in the opposite direction, so it would then become a dash. That inversion of configuration is only occurring, though, at the actual site of attack. It's not going to mess with stereochemistry that is elsewhere. In a SN1 reaction, you are going to be forming a reactive intermediate, which is sp2 planar. So it is not going to have any stereochemistry at that point. So if you have a wedge or a dash, that is going to be lost in your reactive intermediate. And when your nucleophile comes and attacks, it can attack from either direction. And that's going to form a mixture of both wedges and dashes. Rather than showing both, we'll show them as just normal lines and know that that is a racemic mixture. And a racemic mixture is going to be a mixture of both your R and S conformers. When we think about our elimination products, they're generally going to be following what we know as Zaitsev's rule. So we're going to be trying to make our most substituted double bond. There are a few exceptions. If you can make a material that's going to be conjugated, which is going to have alternating single and double bonds, or fully sp2 hybridized, longer amount of resonance, that's going to be favored over Zaitsev's rule, as well as Hofmann elimination. So Hofmann elimination, which I actually spelled wrong, it's actually only one F, and then two N's. So Hofmann elimination is a big, bulky leaving group, especially like a quaternary amine. Depending on the direction of the attack, and our direction of attack is always going to be anti-periplanar. We've shown that how we can draw that in chair structures. Depending on where your groups are located, they are either going to be on the same side of the double bond, and that's going to give a Z configuration, or on the opposite, which is going to be an E configuration. And those are going to be kind of our stereochemistry analogs, like our R and S that we see in substitution. When it comes to rearrangements, our twos are not going to be able to do any rearrangements because that's all happening in a concerted format. So there are no rearrangements in our SN2 or our E2s. For our ones, our SN1s and our E1s, those are both susceptible to a variety of rearrangements. Those are going to give us products that maybe might not be easy to predict if you don't draw the mechanism. These can be due to resonance, hydride shifts. There's also a thing called a methyl shift that we haven't talked much about yet. And those are all possible when we have our ones and we're forming a reactive intermediate. Finally, in terms of competition between our substitution and our eliminations, if you want to push a reaction to eliminate, one thing that you can do is you can increase your temperature. Higher temperatures are going to favor eliminations. Lower temperatures are going to favor substitutions. And that's kind of a big snapshot or comparison between all of these different groups. Now, where that gets a little bit interesting is when you look at a reaction and you're trying to decide what it's going to be, SN1, SN2, E1, or E2. And for that, I have a decision tree that I've kind of made. So this decision tree is posted over in our LMS on Moodle, and it kind of highlights a decision tree or thought process that you'll kind of work through. One of the first things you'll do is identify your substrate. If it is methyl, it's going to be SN2. If it's primary, it's going to go SN2 or E2. If it's secondary, it's probably going to go to any of them. You have no decision. And then if it's tertiary, it's either going to go SN1, E1, or E2, depending on your other components. The next thing we'll think about is going to be with our nucleophile or our base. So nucleophiles, which favor SN2, are often going to have pKa's of their carboxylic acid, of their conjugate acid, which will be on what we'll call kind of like our weaker bases. So we have a bunch of examples here. So chloride, bromide, iodide, cyano, sulfur compounds, phosphorus compounds. If you have a phenyl that has an oxygen off it, that's going to look like a deprotonated phenol. Those can be good nucleophiles for SN2, as well as your deprotonated carboxylic acid, that like acetate. All of those are going to have pKa's, which are going to be kind of favorable to make those better nucleophiles and worse bases. If there's a strong base, and we're going to base that on like a pKa value, for example, it would prefer eliminations. So the bases that will prefer your elimination rather than your substitution are going to be ones that have pKa's of their conjugate acids, which are going to be a lot different. I have a value there for 30 kind of for a point of comparison. Common ones, so hydrides are going to be really good bases. LDA, which stands for lithium diisopropyl amine, that's going to be a really good base. T-butoxide is a good bulky base. DBU is also another base that you can see. I've actually used that a few times in my own reactions. There's some in-betweeners that can kind of go either. So your hydroxide, methoxide, and ethoxides are kind of in between. So if you have a primary substrate, they're more likely to go SN2. Tertiary substrates, way more likely to go E2. And then if they're secondary, they can kind of go either. We then have some poor nucleophiles, and those poor nucleophiles are going to favor your mixture of SN1 E1s. Those are going to be polar protic solvents when you're doing like a solvolysis reaction. So you don't have like a nucleophile, you just have your solvent that serves as your nucleophile or your base. Alcohols, acids, and water are all going to be examples of kind of our poor nucleophiles or bases. And finally, as I kind of mentioned in the last screen too, higher temperatures are going to favor your eliminations. So if you're deciding between a SN1 and an E1, if you see a temperature, which is going to be that delta, that's going to favor your elimination. If I write cold or like 0 degrees C, that might be trying to hint that we're going to do more substitution. And that's kind of a quick snapshot or comparison of kind of like the thought process that I would kind of think about for each of those. So hopefully that kind of gives you a little bit of review on all of these different types, SN1, SN2, E1, and E2. And then in class, we're going to have a big worksheet, which we're going to work through, where we're just going to see a bunch of different reactions, predict is it going to be SN1, SN2, E1, or E2, and then predict the product. So we'll get a bunch more practice in class.